Hello, good evening, everybody. Let's start our today's session. Today we will discuss about some problem of the assignment on medicinal chemistry, which you have already submitted. Okay, so let's start today's discussion. Is my screen visible?
No, sir.
No. Okay, okay. Let me share. Okay, now it is visible.
Yes.
Okay. Okay, so let's start with our today's first question. Okay, so it is saying that which of the following will not be a limitation for pro-drug design. So at first tell me what is pro-drug? How we
Prodrugs are the substances which are inactive but which becomes active after metabolism.
yes, which is in its protected form, a drug in its protected form, which is inactive but it becomes active when it is come to our body or after metabolism, right? So now tell me which of the following will not be mind it there is not be written. Okay, so let's discuss the options given. Okay, so the first one is formation of the toxic product. So will be a limitations for the product design.
Yes, it is limitation.
Yes, it is limitation of the product design. If it is the formation of the toxic product, then we cannot use it as a prodrug. Then toxicity will happen, right? Then an inert carrier can be cleaved off, forming toxic product. Will be a limitation.
Yes.
Yes, this will also be a limitations. And then product leaving off before reaching the target site. This one.
Yes, this is also limitation.
Yes, this is also limitations because if the it is cleaved before reaching the target site, then it cannot the bioavailability at its target site will be very less. So the last option left is the cleaving of the carrier is also site specific. So this
It
is
is the
not a,
advantage.
yes, this is a advantage. If this happens, this is not a limitations, right? Okay, so let's see what is the limitations of the prodrug design is the formation of the unexpected metabolite. The inert carrier can be cleaved off, forming a toxic molecule, and the prodrug might consume vital nutrients. If the carrier cleave is site specific, it can as the advantage, right? As you said. So the prodrug approach seems to be surmount where various hurdles are there in case of the prodrug when we use some prodrug. And what can be the limitations of the prodrug, such as chemical instability, poor water solubility, rapid pre-systemic metabolism, inadequate absorption, and toxicity. Okay. So what is written here? The formation of the toxic product is a limitation for prodrug design, meaning that it is not desirable for the prodrugs to form the toxic products during their conversion to the active form. As we know that the prodrugs are converted to their active forms within our body after metabolism. So a prodrug this is a disadvantage. So therefore the option that will not be a limitation of the prodrug design is the fourth option. The cleaving of the carrier is also site specific. Site specific cleavage of the carrier is actually a desirable characteristics of the prodrug, as it can improve the selectivity and specificity of the prodrug for its target site. thus reducing potential side effects. However, the other three options listed are all limitations that need to be considered in the pro-drug design. Okay, so it is clear to everybody why are we choosing the fourth option, the cleaving of the carrier. It's also site specific. Is this clear to everybody?
Yes, sir.
Okay, then let's move to our next question. Okay, so what is saying here that D1927 contains a branched alkyl group, this one, shown in blue, which protects the terminal peptide from hydrolysis. What is the general term given for a group such as this? So, what we call it? In general term, what do we call it? It is a protecting group, right? Okay, so what is the function of protecting group?
Protect from degradation.
Protect from degradation. Yes, there are various function of the protecting group. Suppose let's discuss with an example. You are aware about the peptide synthesis, right? Some various amino acid joins and then peptide is formed, right? You know what is amino acid and how does peptide bond is formed. Okay, this is the general formula for the amino acid, right? The R may be various substituents depending on the structure of that amino acid. So, how that a peptide bomb is formed? This is an amino acid, and the amide. This is the C terminal of another amino acid. Suppose this is a different amino acid. Then what happen? This NH2 terminal will react with this COOH. Then acid amine coupling takes place, and then water is eliminated, and then amide bond is formed here. Okay, CNH C double bond O, here NH and here C double bond O. Then the rest part is same. In this way, the synthesis continues. Okay, so let's see what is the utilization or what is the need of the protecting groups. Okay, so as we say that this is the amino acid, suppose this is the amino acid, this is solid supported resin bound. Okay, so suppose in side chain there is an NH2. Okay, and there is also a free NH2. Then we are putting a different kind of amino acid, say. Okay, so suppose with this first amino acid, Then we need to couple this second amino acid. So what is our desirable reaction? We want this NH2 group to react with this COOH group, right? Is it clear? Can you get it? I am trying to explain the requirement or the utility of the protecting group. Protecting group not only used to stop the hydrolysis, it can be used to other extent also to protect a group, a functional group from chemical reactivity. Okay, so in this peptide synthesis, we want this NH2 group to react with this COOH group, right? Then only we get the amide bond and the peptide will be formed, the dipeptide, right? Hello.
Yes, sir.
Okay, so now if you follow that there is another some NH2 is there. See, so this NH2 can also react with this COOH group, right? And now if you follow in the second amino acid, there is also another carboxylic acid group. So this NH2 can also couple with this COOH group. So a variety of the reaction can take place. If we do the reaction in the free form, then a variety of the reaction will be formed and our desired product will be in the very less amount. Okay, so to stop the side reaction, unwanted, we use protecting groups. Okay, so now in place of this, if we use, suppose here only this COOH group is open. So now if you can follow that we have protected this NH2 with the NH bog group. So this NH2 group cannot react, and we have also protected the NH2 group of this second molecule with the FMOG group and the carboxylic acid part with its ester group. So now we can you follow that only here NH2 is in the free form, and in the second molecule the carboxylic acid is in the free form. So the only possible reaction is possible between this NH2 and this COOH. So only one amide bond will be formed and we will get only one product in a very high amount. So in this way, by using, then in the next step we can deprotect this group and we can get the free NH2 group. Okay. So in this way, we by using the protection group theory, we can use in our chemical modification reaction. So now let's come back to our original question, that a branched alkyl group shown in the blue line protects the terminal peptide from hydrolysis. So what is the general term given for this group? So is this electronic shield? What about electronic shield? Is this shielding electronically this group?
No,
No. Is this stereoelectronic shield?
no,
No. Is this alkyl shield?
No.
No. So it is the steric shield, right? So the tertiary butyl group present here is very long space occupying spatially. So it is protecting our group coming. So it is so the water molecules cannot come in close proximity. Is this amide bond, and it is protecting the terminal peptide bond from the hydrolysis. So the branched alkyl group is acting as purely as a steric shield. There is no electronic effects. So is this clear to everybody? The what is the function of a protecting group?
Yes, sir.
Okay. So let's move to our next question. Okay. The methicillin was an important penicillin which was effective in the 1960s against penicillin G resistant strain of the S. aureus, Staphylococcus aureus. Although the drug is more effective than penicillin G against resistant strains, it is not as active against strains which are susceptible to penicillin G. The methoxy substituents shown in the red of the aromatic ring play an important role in drug's effectiveness against penicillin G resistant strain. What is the following statement is the most likely to explain? Okay, so what is penicillin? Can anybody tell me?
Which is a beta lactam antibiotic.
Hmm. Which is used to manage and treat a range of the infections. Antibiotic, right? And it is also a beta lactam class of drug. So, which part is the beta lactam in this structure?
Four-member nitrogen containing ring having double bond attached
Hmm.
to the thiazolidine ring.
This one, right?
Yes.
Right? Oh,
Yes.
okay. So, what is our possible mechanism? So, the let's come. The methyl groups act. We are talking about this methyl group, right? Okay, so the methyl groups act as a steric shield to protect the aromatic ring from oxidation by metabolic enzymes in the body. So, can it be true?
No.
Okay. Then, in another options, the methyl group act as a conformational blocker to orient uh, the aromatic ring out of the plane of the side chain amide group, allowing the better binding interactions with the target enzyme. So is this true?
No.
No. The methyl groups increases the electron density of the aromatic ring, allowing better binding interaction with the target enzyme. So this is also
Wrong.
not taking place. So our correct option is the methyl group can act as a steric shield to protect the beta-lactam ring from hydrolysis by enzymes produced by the resistant bacteria. So what are these? Okay, so now the possible explanation. Methicillin belongs to a class of the antibiotics known as the beta-lactam, as we know it, which work by inhibiting the synthesis of the bacterial cell wall. Penicillin G resistant strain of the S. aureus produce an enzyme called the penicillinase, okay, which hydrolyzes the beta-lactam ring of the penicillin G and inactivates it. Now, methicillin was designed to be resistant to penicillinase by incorporating a bulky side chain into the molecule. So, have you got the explanation that this beta-lactam ring is very much prone to be attacked by this enzyme called the penicillinase. Okay, so now uh, this is the main core moiety of the antibiotic. So in methicillin, what strategy we have used? We have introduced the two the steric methoxy group connected to protect this beta lactam group sterically, so that this penicillinase enzyme cannot approach to the beta lactam ring. Okay, is it everybody clear?
Yes, sir.
Okay, other persons, is it clear? Okay, so let's move to our next question. Okay, so why should the introduction of an ester group into the main skeleton of a drug decreases the drug's duration of action? So what is ester group? This is the derivative of an acid, right? Okay, so yeah, it makes the drug more polar and increases the rate of excretion. So is this possible? The first option.
No.
Why not? What is wrong in this sentence?
Polarity doesn't get
Yes,
increased.
polarity doesn't get increased when we introduce an ester group. Okay, in the second one, it increases the molecular weight of the drug and reduces the amount of the drug absorbed. This is also not the right option. And the third one is saying that it reacts with the protein in the body such that the drug is irreversibly linked to the proteins by covalent bond. Is it so?
No. Covalent bond is not irreversible. It is not possible.
Not possible. Yes. So this is not the case. So what is the right option? It is hydrolyzed by the esterase to an alcohol and an carboxylic acid, which are quickly excreted due to increased polarity. Right. So if we break this bond by the enzyme esterase, then the two polar moieties, that carboxylic acid and the the alcohol group is formed. So they are more inherently polar than our original starting ester molecule, and they are excreted from the body. So ester group are susceptible to hydrolysis by the esterase. So what is the function of esterase? It performs the hydrolysis of ester, which are present in various tissues and fluids in the body, including blood, plasma, and liver. Hydrolysis of the ester linkage results in breakdown of the drug molecule into two smaller molecules, an alcohol and an carboxylic acid. These breakdown products are often more polar and less lipophilic than the parent drug. So, what is lipophilicity? I explained in the last class. How do we explain the term lipophilicity of a drug or a molecule?
Which are having a more carbon hydrogens, then which increase the lipophilicity.
What is means the what is the significance of that lipophilicity term? They are
Which are
philicity
called
towards
water.
the lipid.
Yes, yes.
They get
Water heating.
water heating. Yeah, exactly. They will be soluble in the non-polar solvents, like the tendency of the compound When lipophilicity increases, they get solubilized in the non-polar solvents, right? So when they are hydrolyzed to the two polar compounds, polar groups, carboxylic acid and the alcohol, then they become less lipophilic than their parent drug, making them more easily excreted from the body via urine or bile. So whenever they are getting more polar, they will be less lipophilic and they are more easily excreted via urine, right? So as a result, the duration of action of the drug is decreased because the drug molecule is rapidly broken down into inactive metabolites. The rate of hydrolysis of the ester group can be affected by a variety of the factors, including the structure of the ester, the presence of other functional group in the molecule, and the activity of the esterase in different tissues. So, in summary, the introduction of an ester group into the main skeleton of a drug can decrease the drug's duration of action by making it more susceptible to hydrolysis by esterase, leading to the formation of more polar and easily excretable breakdown products. So, is this clear to everybody? Why the introduction of an ester group into the main skeleton of a drug decreases the drug's duration of action? Okay, then let's move to our next question. Okay, megasterol acetate has a short duration of activity since it is metabolized at position 6. Placing a methyl group at the 6th position increases the duration of action. What role does the methyl group play? So what is there in the 6th position? There is a double bond, right?
Yes, conjugation.
Conjugated double bond is there. There is also some double bond is there, and here ketone is present, right? So what it is saying that it is very easily metabolized at position 6. So it is saying that when we are introducing a methyl group in this position, it is increases the duration of action. Okay, so what could be the possible options? It is susceptible to a metabolic group, the first option.
No.
No, because it is susceptible to metabolic group, then it cannot increase the duration
Yes.
of action, right?
Yes. Yes.
Okay, then it is a conformational blocker.
No.
No, because if it is a conformational blocker, then it cannot increase the duration of action. And it is a electron donating group.
No.
No. Okay, so megasterol acetate is a synthetic progestin that used in treatment of the breast and endometrial cancers, as well as to stimulate the appetite in patients with anorexia. However, the acetate has a short duration of activity due to its metabolism at position 6. which results in the formation of an inactive metabolite. So maybe due to the metabolism of this group, maybe due to the breakdown or some adduct forming with the double bond, it is becoming the inactive metabolite after metabolism. So by placing a methyl group at position 6, the metabolism at that position is blocked, which prevents the formation of the inactive metabolite and prolongs the duration of action of the drug. The methyl group acts as a metabolic blocker, which means it prevents or slows down the metabolic process that lead to the formation of the inactive metabolites. Therefore, the correct statement is it is a metabolic blocker. So, in somehow or by some action, it is blocking the metabolism process. So, our metabolism cannot takes place, and it increases the duration of action of this molecule. Okay. So, methyl group is acting as the metabolic blocker in position 6. Okay, is this clear?
Yes, sir.
Okay. Okay, now what sort of therapy involves the administration of an antibody links to an enzyme such that the enzyme activates the prodrug? So, what is the right answer?
Third one, ADEPT.
Hmm. And what does it called? Antibody directed enzyme prodrug therapy. So, what happens here in ADEPT? Sorry. The therapy that involves the administration of an antibody links to an enzyme such that the enzyme activates the prodrug. We know the prodrug is the compound in the protected form of the drug which is inactivated, but it is getting activated inside our body after metabolism. So what is done here? An antibody links to an enzyme such that the enzyme activates a prodrug is called antibody directed enzyme prodrug therapy. So that enzyme is coming to the prodrug and it is making this prodrug a active drug, and this an enzyme which is activating the prodrug is linked to an antibody. You know the what antibody is?
Yes, antibodies are formed against antigen.
Yes, again antigen. Antibodies are basically a protein, right?
Yes.
Okay, so they are formed in against antigen, and then the antigen antibody reactions takes place. Okay, ADEPT is a targeted cancer therapy that utilizes the high specificity and affinity of the monoclonal antibody to deliver an enzyme to the tumor cells. The enzyme in turns convert an inactive prodrug into a potent cytotoxic drug that selectively kills the tumor cell which sparing the surrounding healthy tissues. The prodrug used in the ADEPT is designed to be activated only by the enzyme delivered to the tumor cells by the monoclonal antibody. This minimizes the toxicity of the drug to the healthy tissues and reduces the side effects associated with the traditional chemotherapy. Therefore, the correct term for the therapy that involves the administration of an antibody linked to an enzyme such that the enzyme activates a prodrug antibody-directed enzyme prodrug therapy. So, can you got the advantage of this therapy? Means why it is linked to the antibody? This enzyme, why are you linking with the antibody?
Yes, it targeted the cancerous cell.
Yes, it is very much directed towards the cancer cell. So in many cases, and we know that we are delivered to kill the cytotoxic drug, right? Cytotoxic means which are killing the cancer cell, right? So there are various number of the cell, uncontrolled cell growth. So the drug, what is doing? It is killing the cells, right? Cytotoxic. So now you imagine if this drug starts to kill the normal cell of our body, the healthy cells, then it will be very much problematic or devastating. Then all the cell in our body will be killed by the drugs, right? So what we are doing, we are attaching a monoclonal antibody which is very much targeted against that cancer antigen. So we are that antibody is going to the this cell, and the enzyme linked with this antibody is activating that prodrug and killing these cancer cells, right? So this is the concept of using antibody directed enzyme prodrug therapy. Is this clear? This concept, why we are tagging antibody with the enzyme?
Yes, sir.
Okay. So we are moving to our next question. Okay, cyclophosphamide is commonly used in the anti-cancer therapy. Which of the following statement is not true of the above structure? Okay, mind it is not true. Okay, so it is relatively non-toxic. Is this true or false?
Yes, it is non-toxic.
Yes, you want to say something? Somebody has raised hand. Okay, so it is non-toxic. So it is true, right? It acts as a prodrug.
Yes, it acts as prodrug.
Yes, it acts as prodrug. The structure is metabolized to release acrolein.
Yes,
This is also true.
yes, correct.
And so the false one is it cannot be taken orally. Since it is a prodrug, it is non-toxic to the gut wall when taken orally, right? So this is our desired option. So it is saying that the structure is metabolized to release acrolein. So what is the structure of acrolein? This is the structure of the acrolein. So from here, if you see that by elimination of this part, here this structure can take place in this way, right? Can you follow this? Here double bond will be formed and the whole part is getting eliminated, and here also C double bond O will be formed. So it is acting as the prodrug, right? So our the statement which is not true is it cannot be taken orally. Is this clear?
Yes, sir.
Okay, so in this way, by this elimination of this large group, this pro-drug concept is justified. Means it is eliminating the larger part and the effective drug acrolein is getting out from this big structure. Okay. Okay. Then what is in the next question, that salbutamol is an anti-asthmatic agent which shows an improved activity over previous catechol-like compounds. What strategy was used in order to obtain the improved duration of action? So previously it was, can you tell me what is the common structure of the catechol? Is what it is functional main group of the catechol?
Catechol means there are the two hydroxyl group attached to benzene ring which are ortho to each other.
Yes, very good. So other part is maybe vary, but this is the common part, right? That one is the, that OH group is present which are adjacent to each other. So it is saying that in this improved structure, which is showing the better activity than the our parent catechol compound. Okay, so here it is primary alcohol as it is connected with the CH2 groups, and this is secondary alcohol as this C carbon atom is attached to two different group and one hydrogen, and this is tertiary butyl group. The NH2 is protected with the tertiary butyl group. So the what kind of variation taken place here? The substituent variation. Is this substituent variation? No, this is not substituent variation. Okay, is this chain contraction reaction taking place? Okay, is this chain contraction? No, this is not chain contraction. Here, no chain contraction is taking place. Is this simplification? What is the definition of simplification?
Complex group converts into simpler one.
Yes, complex group coming to the simpler one. So this is or not also not the case. Simplification is not taking place. So a group shift is where a functional group is retained but shifted to a different part of the skeleton. In this case, one phenol of the original catechol ring was shifted one carbon unit away from the aromatic ring. It could also be argued that the strategy was a chain extension since a methylene group has been inserted between the OH group and the aromatic ring. Okay, so can you get it? So in the catechol kind of group, two OH were directly connected with the benzene ring, this OH group. But here we are introducing a CH2 group and then a OH group is coming, the primary alcohol, we are calling it. So this is a common example of the group shift. So our right option is the group shift reaction. Okay, is this clear?
Yes, sir.
Okay, so we are moving to our next question. Okay, so in our next question, we have two structure that chloropropamide has a longer antibiotic activity than the tolbutamide. Okay, so this has the longer antibiotic action than the this one. So which of the following structure is the most likely metabolite of the this one? So what is the metabolite?
Metabolites which the parent compound will convert into another form, which is called metabolite.
After metabolism, right? Okay. So let's consider this structure. Can it be formed from the this one? Here some free CH3 group is there, and here some long alkyl chain is there. So can option B, where the phenolic OH is present here, can it be the metabolite of the this tolbutamide?
No,
No, because here OH group is introduced here, right? And if we consider the option D, then can it be takes place here in ortho position? Some OH group is there.
no, it is also not possible.
It is also not possible. So these two are not possible. Okay, so what may be the common metabolites where the CH3 is present here? By oxidation, metabolic oxidation is a common process, right? So by the metabolic oxidation, either this CH3 group is can be oxidized to the COOH, or this COOH, this methyl group can be oxidized to the COOH group. So it is a very common reaction that the common CH3 group by oxidation it is converted to the COOH group, carboxylic acid moiety. Okay, by the metabolic oxidation. Okay, so let's see what is the more appropriate. So exposed methyl groups are susceptible to metabolic oxidation, as I said earlier, which suggests that metabolites A and C are likely. That here this methyl group is oxidized, and in the C position that this methyl group is oxidized. However, the fact that a chloro substituent in the chlorampropamide, that there is a chloro substitution is there, prolonged activity suggests that it is structure A that is the major metabolite. The chloro substituent in the chlorampamide is resistant to metabolic oxidation. Okay, so it is the structure A. So most probably it is the most possible metabolites taking here. Okay, there are several strategies for stabilizing the susceptible bonds in peptide. Which of the following is not used in this respect? So I have already discussed that we use various protecting group strategy to stabilize that our peptide. So replacing a peptide link with a stable functional group. So do you use it? Mind it, huh? Not used, mentioned here. Replacing a peptide link with a stable functional group. Do you use this strategy? Replacing a peptide link with a stable functional group? Yes, we do it. We very appropriately do it, replacing a peptide link with a stable functional group. You can the peptide link various groups are very much susceptible to the hydrolysis. So if we change this peptide link with a stable functional group, then we can protect our peptide bond, right? So we use it. We use this strategy. So adding a N-methyl group to the peptide link. Do we use it? Yes, we also use it. Sometimes the N where NH is there, then we use the N methylation to stable this bond so that it cannot be taken place to the other kind of reactions. Okay, using an unnatural amino acid. What is natural amino acid? Can you tell me? What are natural amino acids? Hello. What is the number of natural amino acids? How many natural amino acids are there? Okay, there are 20 number of the natural amino acids. We call it essential amino acids, and they are natural, means they are naturally occurring. So, using an unnatural amino acid, yes, using an unnatural amino acid also increases the stability of that peptide bond. So, how it is, you all are known about the amino acid phenylalanine. So, what is the example of an unnatural amino acid? So, in case of the phenylalanine, some phenyl group is present. In case of alanine, only CH3 group is there, and in case of the phenylalanine, instead of one hydrogen, a phenyl ring is there. So this is natural amino acid. And if we change this phenyl group with the cyclohexyl ring, then it becomes the unnatural amino acid. We call this amino acid CHA in short. Okay, so what is the advantage of using unnatural amino acid? They are very much less susceptible towards the proteolytic degradation. As you know that there are various enzymes are there in the body which breaks this amide bond between the two amino acids and the side chain degradation. But what is the advantage of this unnatural amino acid? The unnatural amino acids are very much susceptible towards the proteolytic degradation. So we sometimes use this kind of unnatural amino acid to protect our peptide from the degradation process. So what is the not used in this respect? So in the last option, it is saying that replacing a D amino acid with a L amino acid. So usually L amino acids are the natural enantiomers. Whatever the we used in our synthesis process for this amino acid, they are L amino acids. Okay, in human protein, and so replacing an L amino acids with a D amino acid is often used to stabilize a susceptible peptide bond, not a D amino acid with a L amino acid. So L is the natural one, So if we change it with the D amino acid, then it will be somehow stable. But here the reverse statement is placed here. that replacing D, the unnatural amino acids, with the L, natural amino acids. Okay, so in this way, this statement, this strategy, we do not use to stabilize a peptide bond. Okay, is this clear to everybody? Okay, then let's move to our next question. Okay, so what is saying here that levodopa is used as a prodrug of dopamine since it enters the brain more efficiently than dopamine. So what is dopamine? Can anybody tell me what is dopamine? What is the term used to?
Hormone.
Sorry,
Hormone.
it is a neurotransmitter. So this is basically very much important to keep the neural connections. Okay, so what is the structure of dopamine? Okay, so this is dopamine, and here and some extra COOH group is present here, right? Some carboxylic acid moiety is present here. So we can call it, if this is a drug, this is a levodopa. So if dopamine is the drug, then levodopa is the, what is the common term we can use for levodopa?
Prodrug.
Prodrug. Yeah, prodrug. Okay, so let's. It is, what is the main cause of its better activity of the levodopa? There are various kind of this kind of compound, that levodopa, cabridopa, which are used in various kind of neurodegenerative disease like Parkinson disease, Alzheimer disease. So, what is the cause of using this protected form? It is more polar and crosses the blood-brain barrier more effectively. Is this so?
No,
No. It is less polar and crosses the blood-brain barrier more effectively. Is it true?
no.
No. And it is less susceptible to metabolism. Is this it may be case with the prodrug?
Yes, it may be.
Maybe, but here the more appropriate one is the this one, that it mimics an amino acid, as we know that this is the amino acid kind of structure. We have already discussed in our last question that in amino acid, in one carbon NH2 COOH is present, and some various kind of moiety R is present here. So as you can see that this part is the same, that's NH2 and carboxylic acid, and in place of R, some this kind of moiety is present. So it is maybe the case that it mimics the amino acid and takes advantage of the carrier protein in order to cross the blood-brain barrier. Okay, so due to the its amino acid like structure, it may show some better activity with the carrier protein, better binding activity. So in this way, we can explain this, that what is the cause behind the better activity of the levodopa instead of dopamine. Okay, so this is the right option. So now tell me, L791456 is an anti-arthritic drug. Which of the following solution is not a likely metabolite?
A option.
Why?
Chloride group doesn't convert into OH. In last question, we have seen that.
Hmm. Yes. So here also some N oxidation is takes place. N oxide is taking place here with nitrogen. Some O minus group is taking place. Okay. So here also in the last case, as we have seen that this CH3 group is very much prone to oxidation. That here CH3 is converted to the COOH. That via the metabolic oxidation it may takes place to the COOH. But in case of the option A, that chloro group, here the OH group is present, and as we know a chloro group is very much resistant to the metabolism and is often incorporated in a molecule to block metabolism at a particular part of the molecule. Okay, so comparing the other structure, that in this structure B and C only this N oxide is taking place, right? Here in this pyridine ring and here in this pyridine ring this O minus is taking place. So the structure A is cannot be the metabolite of this compound, as here in place of the chloro some OH phenolic OH group is present there, right? Is this clear to everybody?
Yes, sir.
Okay. Okay. So in the next question we have, why should the addition of an alcohol or phenol group to a drug decreases the drug duration of action? Okay. So polar phenolic or the alcohol group to a drug decreases the drug's duration of action. So in this saying that it increases the polarity of the drug and reduces the amount of the drug absorbed. So what is the right option of this question? It reacts with the protein in the body such that the drug is irreversibly linked to the proteins by a covalent bond. It acts as an electron withdrawing group and affects the binding strength of the important binding groups. So is this an electron withdrawing group, the phenol or the alcohol?
No.
No. So this is eliminated at first. So let's see what is the probable explanation. Okay, so an alcohol or the phenol group is commonly subjected to the phase 2 metabolic reaction, where polar molecules are linked to the group. Right? This is the common characteristics of the phase 2 metabolic reaction we have gone through earlier. Then the increase in the polarity results in the rapid excretion and shorter duration of action. That it increases the polarity of the drug and reduces the amount of the drug absorbed is certainly true, but a reduction in the amount of the drug absorbed is not relevant to the lifetime of the drug in the blood supply once the drug has been absorbed. It would be true to say that the increase in polarity will also increase the rate of the excretion, that it reacts with proteins in the body such that the drug is irreversibly linked to the protein by a covalent bond is wrong. An alcohol or phenol so irreversibly, this is also wrong. An alcohol or phenol functional group is not a highly reactive group, and drugs containing it should not form irreversible covalent bond with the proteins. that it acts as the electron withdrawing group and affects the binding strength of important binding group may be true depending on the structure of the drug is target, but this is pharmacodynamic issue that has nothing to do with the pharmacokinetics of the drug and how long it survives in the body. So what is the right answer?
A.
A. It acts as the polar handle for conjugation reaction. The conjugates are excreted more quickly. As this is the phase 2 metabolites reactions that joining the polar moieties with a group. So it is acts as the polar handle for conjugation reaction. The conjugates are excreted more quickly from the body. Okay, so in the next question, what is saying here? Oligonucleotides suffer disadvantage as drug since they are susceptible to enzyme catalyzed degradation. Which of the following enzyme is mainly responsible for this? Is this peptidases? From name itself, what we can conclude that it is specific for the reaction on what kind of compound? Peptidases?
No.
No, I am asking that what kind of substrate it's peptidases specific for? Like protease acts on proteins. So peptidases
Means peptide bond.
peptide.
Peptide bond.
Yes. Then lipase mainly work on
Lipids.
lipids. And oxidases basically catalyzes the oxidation type of
Oxidation
reaction.
reaction.
Yes, oxidation reaction. So from the name itself, nucleotides, that it is analogous of the nucleic acids. Like some base pairs are there. Okay, so what is the possible option?
Nucleases.
Nucleases. They are responsible for the breakdown of the nucleic acids. Okay, so oligonucleotides are susceptible to the enzyme catalyzed degradation mainly by the nucleases. Nucleases are the enzyme that catalyze the hydrolysis of the phosphodiester bonds in nucleic acids. What is that phosphodiester bond? In nucleic acids, some one base pair is there, then it is connected with the sugar moiety and the phosphate one. So this joining is forming the backbone of that nucleic acid. So this enzyme enzymes catalyze the hydrolysis of this phosphodiester bond in nucleic acid, including oligonucleotides. These enzymes can be present in various tissues and fluids of the body, including the bloodstream, and can rapidly degrade the oligonucleotides, which limits their efficacy as drug. Therefore, the correct answer is nucleases. Okay, got it, everybody?
Yes, sir.
Okay, okay, okay. So, what is saying that there is a structure is given here is an ester prodrug for the candoxatirant, which inhibits the protease enzyme. Which of the following statement is incorrect? Which of the following statement is incorrect? Okay. Okay, so the hydrolysis of the ester reveals a carboxylic acid group in this structure. So is this true? This ester group?
Ye-
Yes,
Yes, yes, it is true.
yes. Obviously, by breakdown of the ester group, a carboxylic acid moiety will become free, right? Okay, so the bicyclic leaving group is non-toxic.
Yes, it is non-toxic.
Yes, it is non-toxic. So it has to be non-toxic, otherwise it cannot be used. If the side product is the toxic one, then we cannot use it, right? So the parent drug cannot be administered orally, whereas the ester can't. Is this true?
No,
Okay, so let's see. The bicyclic system is electron donating and speeds up the hydrolysis process. Is this true? The last one?
no, it is not true.
Okay. So the bicyclic system present in the structure of that carboxyl serves as the lipophilic group, okay, which increases the overall lipophilicity of the molecule and facilitates its penetration across the biological membrane. So as we know, the biological membranes are the lipid containing. So whenever a molecule is the lipophilic or increases its solubility in the lipids, so it speeds up the membrane penetration. It does not speed up the rate of ester hydrolysis. Okay, upon hydrolysis of the ester prodrug, the resulting candoximine molecule inhibits protease enzyme, which can help in the management of the conditions such as hypertension and heart failure. The other statements are correct. That hydrolysis of the ester reveals a carboxylic acid group. The bicyclic system leaving group is non-toxic. The parent drug cannot be administered orally, whereas the ester group can be. So the other statements given here are the correct, but the last one, that it speeds up the rate of the ester hydrolysis, this is not true, because this part is the responsible for the lipophilicity and helps to enter in the lipid membrane. So this is our incorrect statement. Last one. Okay, so that's all from today's session. So if you have any doubt or any query, you can tell me. Otherwise, let's meet in the next class.
Thank you, sir.
Okay, thank you for joining. Let's meet you in
Thank
the
you, sir.
next class. Next class. Okay, thank you. Thank you.